Hello, everybody. So today we're going to be focusing a little bit on the thermodynamics of mixing liquids together. So this is going to take a lot of what we've learned so far about the behavior of liquids and combine it with a little bit of what we've touched on with the thermodynamics of mixing gases. So a good place to go ahead and start is our more general equation of essentially the chemical potential or molar free energy of a species of an individual liquid species. And so ideally we can examine a uh, volatile system by knowing the chemical potential of the pure state and knowing the ratio of the partial pressures of the gas compared to the vapor pressure of the pure species. Now, we're very lucky, and we're going to go ahead and try and start on a simple scenario, which is ideal solutions. And so again, these are going to be solutions that follow Raoult's law, where the intermolecular forces of the two species are fairly similar, and so that um, species A will pretty much act as if it was surrounded by species A and not B. So under these cases, we can go ahead and give the chemical potential of A simply by knowing the chemical potential of the uh, pure liquid, which is often available through thermodynamic tables, but can be calculated by other means, and simply by knowing the ratio of the two species through the mole fraction. So this is actually a fairly nice expression that we can make use of. And we can go ahead and combine our two chemical potentials to generate the free energy of the entire ideal mixture. So in this case, we're simply going to be taking our chemical potentials, which again are just molar free energies, multiplying it by by the amount of each species, and then adding together these two free energy terms together. Now we can go ahead and combine this with our expression of an ideal solution. So in this case, what we end up having is both of the two species are described by the chemical potential of the free species times the amount, as well as essentially this correction for essentially the mixed species. Now, what we can do is go ahead and examine the Gibbs free energy of mixing by essentially taking the free energy of our mixture minus the free energy of the pure system. Well, this actually ends up being a quite elegant expression because it turns out that the free energy of the pure species is just going to be the amount times their chemical potentials. Well, you may notice we have a couple of shared terms here. And so what we're going to find is that the energy terms of the pure species are going to essentially drop out when we're looking about this mixing process, as they essentially represent the reference point, which essentially just helps us go from a kind of artificial free energy term to what we almost always care about, which is changes in free energy. So when we do this, what we get is a special component left behind, which is going to be that the free energy of mixing is going to depend upon, of course, the amount of each species and the temperature, which again makes sense because of the temperature dependence of free energy, and literally just the ratio of the species, again, as exhibited by the natural log terms. Now, let's be honest, it's a little bit annoying having to make use of the total amount of moles, especially as this is a size extensive property, and we much prefer to change it to more size intensive property. And we can do this simply by expressing the moles of A and B in terms of the total moles and the mole fraction, at which point you can go ahead and change this expression to a molar Gibbs energy of mixing simply by dividing both sides by the total number of moles, which is quite an attractive option. So this gives us a relatively nice description of the free energy or favorability of mixing a species. Now, one of the things that I want to make note of is that when I'm looking at the mixing of two ideal species, just like for mixing of ideal gases, we expect our natural log terms to always be in between 0 and 1, indicating negative values. And again, with the mole fractions and total number of mole fractions being between 0 and 1, we're going to notice that these terms will always be negative, indicating that from this perspective, we would expect for an ideal system, the Gibbs free energy of mixing to always be favorable. We can also use this to generate a free energy of mixing simply by taking we can use this to determine the entropy of mixing simply by taking the temperature dependence of the free energy of mixing. Again, with a little bit of a throwback to our thermodynamic equations. So by taking the isochoric, because we're looking at free energy, temperature dependence of our free energy, what we're going to notice is that as we have a linear dependence on temperature on both components, we'll essentially just watch the temperature dependence wash out, and we're just going to be left behind with a rather simple and elegant description of the entropy of mixing in terms of the mole fractions of each component and the total number of moles. And again, because the mole fractions between 0 and 1, our natural log term will always be negative, generating a net positive entropy of mixing, which again makes sense as I'm going from a mole fraction of 1, which is a highly organized system, to a mole fraction less than 1 will always be a favorable process in terms of entropy. But what we can also do is use this to determine the enthalpy of mixing. So what we can do is rearrange our free energy relationship and notice that the enthalpy of mixing is going to be given as the free energy of mixing plus the temperature times the entropy of mixing. Well, you may notice here that these two expressions look rather like each other. So if I multiply my entropy of mixing by temperature, well, it turns out I have the exact same expression, just with a negative sign. So it turns out our enthalpy of mixing for this ideal scenario is 0, which again is important to note because this is going to go back to our definition of an ideal mixture. Because we started this idea assuming that we had an ideal system, more or less that it obeyed Raoult's law. And one of the important ideas about that is the intermolecular forces of the two species are the same. So if my intermolecular forces don't change, my enthalpy won't change. And this generates an enthalpy of mixing of 0, and thus essentially this relationship in between entropy and Gibbs free energy. And again, this makes sense because if I had a non-zero enthalpy of mixing, we'd expect a term out here that showed no temperature dependence, again, indicating an enthalpy term. So we actually now have 3 simple equations that do a pretty good job of describing an ideal mixture, but again, we're not always dealing with ideal systems. So what we really would like is to be able to take these tools and try and turn them into a non-ideal system. And so we're going to more or less use a classic PChem trick, which is using a fudge factor. And this time we're going to call it the excess function. And this is going to be applied for more or less any thermodynamic feature, but we're going to focus on using it to describe mixing. So the excess function for any thermodynamic variable is just going to be the mixing of that thermodynamic variable minus the ideal scenario. But again, you can apply this to any process, any change minus the ideal change. So for example, let's go ahead and focus in on one of the most notable approximations of an ideal system, which is that the enthalpy essentially behaves ideally, or that my enthalpy of mixing is 0. So in this case, the excess enthalpy is going to be a relationship in between the actual enthalpy of mixing, so how much the intermolecular forces actually change, minus how much they change under an ideal scenario. Well, again, we just proved that the enthalpy, the ideal enthalpy of mixing is 0, so this actually is quite a nice description for enthalpy. as our excess enthalpy is simply going to be the actual measured enthalpy of mixing. And this will essentially give us an indication of how much we deviate from ideality, which again is a very useful feature. Now it's worth noting that this treatment is a little bit more messy for entropy and free energy, as both of these functions are going to have a non-zero ideal value. So as we deviate, so their deviations from ideality get a little bit more messy, as I actually have to subtract something out from the measured value. That said, a classic approach to try and look at excess functions and ideal systems is to move away from ideality very slow. So one of the simplest features that we can kind of look at excess entropy and free energy is going to be to look at what's called a regular solution. So this isn't a solution that eats its fiber. This is essentially a solution that's going to be actually fairly well mixed. So in other words, I don't see any pockets or clumps of A or B, which would indicate that it's going to be just as well mixed as if it was ideal. But we're also going to be assuming that the excess enthalpy is non-zero. So in other words, we're going to have a well-mixed solution, but we're going to have some degree of intermolecular forces. And as soon as we include intermolecular forces, this means that mixing of our two systems is either going to release or absorb heat. And this is going to be a very important thing to take account for. So if I'm going to be looking at excess enthalpy, it turns out we have a fairly good description to provide our excess enthalpy. And this is essentially going to be based on a variable xi. And essentially xi here is going to be a measure of the intermolecular forces of my complex relative to the pure species. So if I take AA and BB, combine them together to make AB, is it going to essentially be endothermic or exothermic? So if my xi is greater than 0, this is going to indicate endothermic mixing. So essentially, we'd expect heat to be released, and this is usually going to be due to the fact that AB is relatively unstable. So I'm mixing two species that just don't want to hang out together. So a good feature here would be something like oil and water. If xi is less than 0, then this is essentially going to indicate exothermic mixing, as AB is going to be a very stable combination. So again, this is going to release heat, as I'm going from a high energy AA species or BB species to say something that really wants to hang out together. So in conjunction to the systems we've already examined, this might be something like chloroform and acetone, which, because they can make better polar bonds to each other than themselves, really like to hang together. And so we'd expect to see a xi of less than 0. And here, what we're also going to show is that essentially n times the two mole fractions is going to represent, to a great extent, the frequency of interactions. So if I have a xi of 1, if I have a mole fraction of A of 1 and a B of 0, well, this indicates that I'm not going to have any interactions. So my enthalpy excess is going to also be 0. If I have a mole fraction of A of 0 and B of 1, then again, no interactions. And just like we've seen before, interactions are more or less going to maximize when these two mole fractions are as close to each other as possible. So 0.5 and 0.5 is going to maximize that whatever xi we're seeing is going to happen as frequently as possible. It's also worth noting n here is also present to indicate how common the interactions occur. In general, how much overall A and B do I have, as well as we have to account for here that enthalpy is given as a size extensive property. If you want to go ahead and turn enthalpy into a size intensive property, you can give molar excess enthalpy just by dividing both sides by n. Also important to note that here, temperature will also feature into the enthalpy due to the frequency of collisions, as we expect interactions to occur more rapidly under high temperature, as everything's going to be moving more and thus seeing what else is around much more frequently. So if we go ahead and examine this system, what we're going to see is that, say, if I have a negative xi, and I'm looking at an exothermic reaction, we're going to see the most amount of heat, or the negative enthalpies, around a mole fraction of that 0.5, because these collisions are happening very frequently. However, let's say I have a common system where where my molecules tend to like to hang out with themselves, which tends to be a little bit more common than an exothermic mixing. Well, in these cases, I'm going to expect the reaction to occur I'm going to expect the system to essentially require the most energy to drive that mixing around, again, that 50 mole percent mixture, because that's when I'm going to have to force them into proximity the most often. This is going to have some very important consequences for the favorability of a mixture. However, if I'm looking at how favorable a mixture is, I'm really barking up the wrong tree with enthalpy, though it will give us some insight. Because if I'm looking for favorability of mixing, for that, I really have to go to Gibbs free energies. And so if I'm looking for a non-ideal mixture, I'm going to be looking at how much it deviates, again, from ideality. So I'm going to need to use my excess functions. And in this case, the Gibbs of excess can be given, again, as the enthalpy in terms of the enthalpy and entropy of excess. And if I'm looking again at my regular solution, by definition, the entropy of excess is 0, and we already just provided a function for the enthalpy of excess, which means that under this scenario, for a regular solution, the Gibbs of excess is going to be the same thing as the enthalpy of excess. So we essentially just get our function right on back. Now, in this scenario, what we can do is look at the free energy of mixing and its favorability by, again, combining what we know about ideal behavior with essentially this extra fudge factor of non-ideality, or my Gibbs of excess. And when I combine these two functions together, what we end up with is an expression that combines the natural log of the two mole fractions, as well as essentially just the straight multiplication factored in by this strength of the interaction. Now, again, it's worth noting that this is going to be a size extensive property. And if I want to make it more size intensive, we can divide all sides by the common shared total number of moles, which is going to be much more useful for a real system. Now, this is a little bit of a kind of big expression, so let's go ahead and try and take a look at how this would behave. So what I have is my entropy of mixing is essentially going to always favor mixing. So I'd always expect a negative Gibbs energy of mixing if I was just looking at this entropic term. However, what ends up happening is that I'm essentially going to be modifying that by this enthalpic-based term with its associated xi. And the more endothermic the reaction comes, essentially the less the A and B species like each other, the more positive this value becomes. And what I'm going to end up seeing is this factoring in of essentially a disfavoring of mixing that maximizes around that 0.5 mixture. And this actually really starts to pronounce once my xi essentially exceeds a value of 2. Because once I exceed a value of 2, what we end up seeing is an inversion of the behavior around this even mixing component. Because while entropy essentially says I'd like to be perfectly mixed, when I start driving these interactions to become more and more common, I'm essentially having to pay more and more energy to make those interactions happen. And entropy just simply can't do it anymore. And so at this point, what we do is we change the most favorable point of my free energy from being this 0 point to essentially being 2 points on either side. And so if I go ahead and mix A and B with a xi greater than 2, and if I mix them in a 0.5 mixture, turns out I actually won't end up with a perfectly mixed species. Instead, what I'm going to produce is two mixtures with essentially inverse relationships in between the mole fractions of A and B. Because what's going to happen is that I'm not going to want to form this even mixture. I'm going to want to form something where B is mostly seeing itself, and A is mostly seeing itself, because that's what's going to make the enthalpy happy. However, because entropy, in a sense, always wins, these are never going to essentially be pure A and pure B. Now, what we often think about is when I have things like oil and water that we say don't mix at all, what we're really looking at is a system where xi is very positive. And as we get more and more positive, these mole fractions essentially creep closer to 0 and 1. But they will never ever reach 0 and 1. So I'm always going to see some sort of mixture of A and B, but where these points are going to land is often very dependent upon the strength of your intermolecular forces. So hopefully this makes sense, and we'll take a little bit more look at some mixtures next time. Till then, take care.